Okay, good afternoon, everyone. Let's get started with our second lecture of NLP. In case some of you have just decided to enroll in the course, I want to reintroduce myself. I'm Professor Anna Marasovic. I use she, her pronouns. I am going to be your instructor, but I'm also researching large language models, which will be focused on this course. And I focus on their interpretability and how we can use them and combine them to provide AI assistance where it's needed. We have two TAs. One of them is Nate. I see Nate over there. He's waving us. Ro, he is a PhD student working with me, also researching interpretability. And your other TA is Raiko, which I know is here, but oh, there it is. And Raiko is going to be your other TA, and Raiko is a first-year master's student who is also doing some research with me on web agents. I finished last lecture by saying you are responsible for understanding everything that's in syllabus. So yes, you must read it carefully. I went through some things that I wanted to highlight. I didn't highlight one thing, so I'm gonna go over it now, which is what is my stance on using generative AI. And my stance is that basically I tell you how I expect you to collaborate with other students in this course. And I would love if you know each other and talk to each other and collaborate, of course. But that doesn't mean that you can together write a solution and submit it as a unit. Rather, you can discuss, okay, oh, I would approach it like this or that. And then when it comes down to actually writing your code, you should write it yourself. And I am okay if you use generative AI in a similar way. You are doing your homework and you want to approach it the way you would approach another person, not asking, hey, give me your homework, give me your solution, I'll submit the same thing. You want to do that with your peer a classmate, and I don't want you to do that with generative AI either. But if you are debugging and you're getting stuck and you want some assistance, the way you would ask your friend what could be a problem, that's okay. And of course, if you actually manage to do something, but maybe you are unsure, like why this change work, you can also consult generative AI as you would your friend in a class. And of course, we are here, we will have office hours, so we are happy to help you with both of these things too. All of the graded components of this course are proctored, so I don't suspect that the generative AI will be an issue, big issue, but I do want to encourage you, or I wouldn't say I demand that you use it in the way I said you should use it just now, but basically, because you then have these graded versions, if you have no idea what the AI has generated, that won't help you at all, because in the end, you come here and you are going to implement a related task to the homework. Please read the academic misconduct policy, understand what does it mean, what is a misconduct in the School of Computing, and what is the process for academic misconduct. It's all written in these links in big details. I did highlight some of the stuff that you should know about, such as strike system, and also like if you are here and unfortunately you consult your peer in a way that is not allowed during exams, and we take your exam, you're going to get 0 for that exam. And the way that the grading scheme works is that then you need to have very high scores in all of the other components of grading. And I emphasizing this because unfortunately, when students come into this situation that tell, oh no, but because I failed this exam, I'm going to fail the course. And because I failed the course, I will, this and that. And that's too late. Once we determine there is a academic misconduct, we can't revert it. So I would really warn you against doing anything that would be academic misconduct in this course. Okay, now that's a little bit negative sounding. So let's move with more fun topics. And before I do that, are there any questions about the logistics of the course that I didn't mention that you would love to hear a little bit more about? Yes, please.
I heard that there's a class on explanations for explainable AI. if you had taught, is there a separate class on sustainable AI?
Not this semester, but there will be one next semester.
Is it? There will be next.
Yes, yeah,
Credits.
Yeah. That's right, yeah. The only reason why it wasn't offered last spring is because I was on the teaching release, yeah. So every spring, basically, that course is going to happen, and it's going to become a little bit more refreshed with some new mechanistic interpretability stuff, yeah. So that's gonna happen for sure. And if you finish this course, you should definitely enroll because it's going to be a super nice extension of, going into depths of the LLMs that you learn here. Okay, so I said we are going to focus on large language models, which are basically deep learning models of certain kind, which means that we do need to understand a bit of deep learning. And I told you that deep learning is one kind of machine learning. So what I'm going to do in the next couple of lectures, because no sorts of ML is yet a prerequisite for this course, I'm going to give you a crash course on basics of ML and DL, deep learning that you need to know, okay? And it's going to be, I will try to not go as fast as I did last year, which was apparently extremely fast, but it's going to be, if you never heard about any of these concepts, it's going to feel fast. I acknowledge that because there's just a lot of new stuff to hear, but so it is, we need this to know what LLMs are, and we can't go in depth of this because that's the job of machine learning and deep learning courses. Okay, so the goal today will be to go over and learn components of a supervised machine learning system for binary text classification. And I'm going to start first with an overview of the 4 components that you need to develop a system that will be capable of doing text classification with a supervised machine learning system as a backbone. So that's our first topic for today. Let me introduce the sentiment classification task. Sentiment classification is a task where you get a piece of text and you need to determine the sentiment of that text. Now, sentiment isn't a super well-defined concept, but very often you will see it in a very crude form of predicting whether the text is either positive or negative. And we are going to embrace this kind of notion of sentiment classification, classifying a text into positive or negative sentiment class. Okay, so this is going to be our example, and it's a very well-studied task in NLP. Okay, so the first component of our supervised machine learning for binary classification tasks, such as binary sentiment classification, is going to be to turn our piece of text, such as this movie review, into a vector representation of that input. Why do we do that? Why don't we just say this is a Python string and use this data structure as a way to, figure out what the sentiment of this text is? Well, our computers, they don't process words as humans do, right? They process numbers. So we do need some numerical representation. And that numerical representation of this piece of text should capture important features of this text, such that our supervised machine learning algorithm can iteratively recognize some patterns in this piece of text that are associated with certain labels. For example, seeing a lot of positive words, so words like good or great or amazing, will likely be associated with a positive sentiment label. And your machine learning model is going to recognize that from the labeled examples you give it to kind of learn these associations between patterns and the label. So basically, whatever numerical representation you choose has to have useful features of inputs, such as some of these numbers need to indicate that in the case of sentiment classification, that some positive word has occurred in the input. And today we are going to cover some ways of how to build this high-dimensional vector of input, where these features are quite explicit. We are going to manually define them. And as we progress in this course, we are going to lose that manual intervention, that defining of what the features are, and those features are actually going to be learned from the data, and we are going to lose some interpretability, and this is why we have the interpretability course, then later when we build these LLMs that we can poke around and see what kind of patterns the model is actually using. Okay, so first step, we can't work directly with the string. We need to produce a vector representation of our piece of text, and this vector, these numbers in this vector will be associated with useful features of this piece of text. The next component will be that we need some kind of classification functions that decides which class to apply to an instance. So here we have our piece of text, we transform it into vector. Basically, we need some function of that vector that tells us, hey, is this positive or negative? And mathematically, we can write this down like this. So we are looking at a value I hat, which is a decision whether this is a positive or negative sentiment class for given this input. And this is going to be based in this course on the notion of probability. So we won't just have a classification that gives us this is positive or negative, but we want some notion of how likely is that this is a positive example of a positive class. And therefore, this classifier is going to be probabilistic. So we are going to go over how we can define that. And today we are actually going to learn one such function called perceptron. Yeah, I guess that's it about that. Okay, so once we have this function, we will need to optimize the function's parameters. And this is where machine learning comes from. So yes, here we have this function, but it's not fully defined yet. Basically, first thing you do in machine learning, you decide, I'm going to take a model of a certain kind to model my problem. So maybe you restrict yourself to linear class of models, like in this example here. So in this example, we have two classes, two blobs of data belonging to two different classes, a blob here that's positive and blob here that's negative. And we have said, okay, we are going to restrict ourselves only to linear models, meaning a line in this 2D space, right? So if we decided, okay, it's going to be a line, then line can be defined as ax plus b, right? And that's how it's defined, but we don't know what the right a and b are to separate these two clusters. So here we have I equals, so the line is minus x plus 9. So we have these two parameters, a equals -1 and b equals 9, and those are good parameters of a linear model, a good solution to this problem for the training data. Here, on the other hand, we have 0.8 and 4, and here this line then doesn't separate these classes well, and those are bad parameters or weights. And similarly, here where it's not perfect, but it is better. Okay, so basically in a previous step, you have set my class of model I'm going to choose. It's, let's say, a linear model. It's not always going to be a linear model. This is just for the sake of this today's lecture. And I don't know which linear model is good. I know that the line will be good enough here, but I don't know which line exactly. And the goal of machine learning is that by giving this data, this labeled data, these data points with labels of whether they are positive and negative, that we iteratively change this line, try a little bit like this, move it up, down, rotate it, until we find parameters A and B, which separate this problem perfectly. So here the loss is 0 because no data point is misclassified. Here it's 17 because 17 points are misclassified, and here it's 2. So you can imagine you randomly chose A and B as your starting point, and you get, ooh, error is 17, that's a lot. So then you tweak A and B in some clever way, such that the next time in the next A and B you get will give you a line that's slightly better, and maybe you get this line, and then you try again, and you come to this one. Okay, so to do that, to do this like, oh, I'm iterating and changing, we need this concept of some kind of objective function. Like, what do we want to improve by changing the parameters weights A and B? And here we want to change the error or the loss of the classification of our training examples. They are labeled, we know exactly to which class they belong. So we can check, hey, did I, in this iteration of choosing the parameters A and B, chose the right thing, or now we have error, and you are trying to iteratively change it. Okay, so let me see, I have some piece of text here. So usually a thing we want to use to change our parameters or weights in a way that they are going to be a better solution to a problem is a sum function corresponding to error on example, such as the difference between the prediction probability we give to the class label we know the example belongs to, and the true probability for that class, which is 1, right? If you know that the example belongs to sentiment positive class, then the probability for positive sentiment class should be 1. And if we have given it like 0.1, then we have huge error of 0.9. But if we are very close, we have given it 0.9 and should be 1, then the error will be only 0.1, which is much, much lower. Okay, so once we have that, we are going to then use some optimizer that some numerical mathematicians have developed to actually tweak these parameters such that this function is lower, typically lower. And here, it's important to recognize that we are using information about labeled data. So our data that we are giving to this model to learn from, it has labels for each training example. We tell it you are positive or negative. And then we can use that information to define the objective function and change these parameters and weights. Because we are using this labeled data that some person or group of people had to manually label, which we call annotation, then this is an example of supervised machine learning. So supervised is referring to the fact that our training data has labels that were written by some people. These days, this becomes a little bit messy because today we are using syntactically generated data with LLM generates this label, but the principle is the same. You are using labels, right? Either them coming from a person or an LLM today isn't so important. All of that is supervised machine learning. Okay, final piece of a puzzle, of course, is that we have an algorithm for finding which parameters and or weights are appropriate given our objective function. And here, maybe thinking in like what you know about math, so far you might be thinking, okay, I will use some closed form solution. There will be, my objective function will be some formula, and I will have a closed form solution to that formula. I will be able to give A and B such that I have a guaranteed that those A and B for my linear model are those that minimize this objective function. And that's almost never the case in modern machine learning. We don't have this nice closed formula. Rather, we start with some random guesses for A and B or other parameters and weights. And we measure what's the value of our objective function, like error and loss, what is it? And then we use algorithms that tell us how we should change A and B such that the objective function is lower. And then we get new value for the objective function, and we try it again, like we change A and B such that it's even lower, and even lower, 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 until we maybe recognize that we are not managing to lower it anymore. We kind of have a plateau, and then we would stop. And later today or next time, we are going to talk about one such optimizer that's heavily used, or it's a building block for the most commonly used optimizer called Adam today. Okay, let me let me go over this and then I will go over phases, or maybe I should do the phases. Okay, let me cover this. So the four components of supervised machine learning for binary classification I mentioned are: we start with a piece of text, and we don't put that piece of text as a string in Python and call it a day. Rather, we need a numerical representation of that text that captures important features that a model can use to find connection between features and labels, such as positive word, positive label. So we are going to turn our text into a vector in some ways that we are going to learn today and more throughout this course. Once we have done that, we are using some kind of classification function that decides what class to apply to an instance. So far, I've been using an example of a linear model. So we deem that linear model will be sufficient for the problem. We say we are looking for a line ax plus b to solve this problem, but we have no idea what a and b are right. So we are looking for the values for these parameters or weights a and b. And to find those good values for a and b, we will need an optimization function, which will tell us, well, if you, which we can use to kind of change a and b such that this optimization function is better and better and better. And to do that tweaking of a and b to make the objective function better, we need an optimization algorithm that's going to do that for us. And I said that we are going to use iterative algorithms rather than closed form solutions. One thing I want to mention before I stop and ask you whether you have any questions is that supervised machine learning typically has these phases. So the first phase is training, basically what I've described so far. You give some labeled examples to the model to learn useful patterns between features and labels, and we find those good values for parameters and weights that minimize the objective function. So once you have done that whole process, you can do what we call model selection. So later today, you are going to see how many decisions you as a developer of a machine learning model need to make to develop a model. These parameter weights, they are learned from the data. But then there are these hyperparameters, things you just simply need to decide. And there is no right answer for what the right hyperparameter is. So what we do is we define our model, multiple versions of it with these multiple hyperparameters. As an example of hyperparameters, I said that we are going to iterate over the training data, but you can set as a hyperparameter how many iterations you're going to have. Maybe you deem 10 is enough, maybe you deem 100 is needed, whatever. All of these can be different training runs of the same model. And you can use what we call development data to check your performance of various training runs. And then you can select the one which is the best on the development set. That's an example of model selection. Once you have done that, now you need to check whether your chosen model works well on what we call held out set of examples. Held out because it wasn't used for training, it wasn't used for model selection, it wasn't used for anything. And this is called test set. On the test set, you are then going to measure your model's performance, such as accuracy and F1 score that we are also going to touch on. So these are three common phases of the supervised machine learning. Okay, before I move on, we are going to go in depth of every one of these components. Are there any questions? Do you feel like you kind of understand the workflow here? Yes, please.
To clarify, that development set in the model selection, that's a set of data separate from the training set?
Yeah, exactly. So just to visualize, you have, this is your entire set of labeled examples you have. You will choose most of it for training. So this would be training, most data you need for training. you will use a portion of for development and then portion for testing. Yeah. The idea is that this part is completely held out because you want to give the most fair and reliable estimate of your model's performance. So now, because you have tweaked your model to be as best it can on this data, now the question is, but what about some other data? Will it still work? Will it still be really good there? So we always want to make sure that this part is completely untouched. Right. Yeah. So completely held out, and then you don't want to overlap between these because you're using optimizer to be extremely good on the train data. So again, you want to have some notion of like, how does it generalize to unseen instances, and therefore you have a depth set. Yes.
So for the training data, I'm assuming we're also setting it to a vector that we're then going to apply our objective function to.
Yeah, but with one clarification, maybe you already have this in mind. You're not using one representation for all the examples in the training example. Rather, each one example is getting its own vector representation. Okay, so each one is getting a vector because we are not classifying the entirety of training data. We are classifying each example individually. Yeah. Something I didn't mention here, but it's important to mention, is the concept of generalization. So when I defined machine learning last time, I told you it's an algorithmic field where we try to make algorithms that can predict something that's going to happen basically in the future, right? So you have seen this example during the training, but the goal is that your model performs well for something that might come later on. And this test set, which is held out, is kind of mimicking that, something you haven't seen yet, but might see in the future. And still in the future, it should behave well for those examples. And this is basically generalization. You want your model to perform well on unseen instances, and we refer to that as generalization. Model should generalize well. That's like a holy grail of machine learning. Okay, so we have these 4 components, and now we are going to go into each one of these. All right, first of these is going to be a feature representation of the input, which means from this one single piece of text, you want to produce a feature vector. And while we talked about this here, it might seem like only training examples get feature vectors. No, everything gets a feature vector. So development example also will be represented as a feature vector. Test set example is also going to be represented as feature vector. So basically, when we say we classify text, a piece of text into positive, negative, we are actually classifying feature vector representation, right, into positive and negative. And today, I see you, just a second. Today, we are going to cover a few ways of doing that that are not the way we are going to be doing it with LLMs. This is just a first intro to how to do something like this that you're going to implement in your homework but then later on, we are going to do this entirely differently. Yeah.
How do paragraphs of different lengths get transformed into the feature vectors of the same size?
Same size. Let's go back to that question when we see some examples of how we do it, because I think you are having some idea of how it might be working, but it's not the case that as many, let's say, words there are here, that's going to be the size of this vector, and then the next vector is going to be shorter or longer. We are not going to do that. Yes.
For the training data, is it do we give it the feature vector representation, or does the program make it retroactively to the training?
So first, like each training example is a separate thing, which we then transform into a feature vector. You, as a programmer of your machine learning model, you are going to decide how that's going to be produced. And now we're going to see some examples of how to produce them. So let's maybe hold on and see some examples, and then I'll check whether it's clearer how we go about this. So let's maybe move on. I feel like, of course, I'm happy to see there is, interest in how we're going to do this. That's great to see. But a lot of questions here and doubts you might have in mind is probably going to be answered by looking at examples. So first thing, before we do actually produce this vector, we are going to tokenize our text. And if you remember from last time when I bombarded you with like a gazillion pieces of information, I told you that we are going to split a string into a sequence of tokens, because if we wouldn't do that, if we were trying to find a great vector representation for every single piece of text in English, we would need to find a way to produce infinitely many such things, and that's gonna be hard. It's easier to split your input into tokens, words, something like the unit, and then find a way how to combine these units to make a decision. That's why we are doing the tokenization. And token is basic units which need not to be decomposed in a subsequent processing. Now, what doesn't need to be decomposed further, it's up to discussion. In English, which is words are nicely separated by white space, a logical maybe thought here is to just use white space tokenizer, where you split them. For example, this instance, this film is interesting as an experiment, but tells no cogent. How do you pronounce this word?
Cogent.
Cogent. Okay, story. So if we split it by white space tokenizer, this is a list we are gonna get. And this makes sense for English. For some other languages which don't have a white space to delimiting words, such as, let's say, Chinese, this wouldn't make a lot of sense. And maybe you would say, well, I would actually rather use character as a way to decompose a piece of text, or maybe your language wouldn't be, either of these things would work for whatever language you are interested in. For the sake of today's lecture, and all the way until we start talking about transformers and LLMs, we are going to talk only about white space tokenizer, but then we are going to, as soon as we start touching on LLMs, we are going to change in something we call subword tokenization, and how to split these sentences or larger pieces of text into tokens that can be subwords of a word, such as like prefixes and suffixes. All of that is going to be a separate token. But for now, let's talk only about white space tokenizer. Can you tell me already what an issue here is with this tokenizer? Yep.
When you have each of the words kept separate, you lose some of the context that those words might have.
Okay, but we can later on allow some, okay, you can check what this word is. We can do something extra on top of tokenization. Is just about splitting. So you will never, you can't split a piece of text such that now this unit that you have used knows something about the other unit, right? Like that's not possible. You can just split it, and later you can allow some interaction, right? Yeah.
Maybe some of the words don't have meaning.
Some of the words don't have meaning, so you would just discard them, right?
Yeah.
But we can do that as post-processing step or pre-processing, depends how you call it. Yeah, so that isn't really an issue of tokenizer. We can add that as an additional thing. Yeah.
Like this with a comma is the same meaning as this without a comma.
Yeah, so story period is now just a single token here, whereas we know that these aren't a thing that should be together, right? It would be better if you have story and period as a whole separate token. So, for example, if I had sentence like, this film is interesting, blah, 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 and then story and exclamation point, I would now lose information that story was shared in both of these pieces of text. Yeah.
You have like, like past tense or like plural or in the present, and then like that would just increase your vocab size.
Yeah, exactly. So this is something we are going to talk about later. But basically what you're referring to here is inflecting words. So we add suffixes, prefixes to words, but basically the core, the lemma of the word is shared. And now if for every inflected version, you have a separate token and later on separate high-dimensional representation, you just need to learn more things and you're losing information that these things are shared. For English, it's going to be a less serious issue because in English, we don't inflect words so much. We would say that English doesn't have rich morphology, which studies how we inflect words. In other languages, for example, again, Croatian I'm a native speaker of, we have declension, meaning changing of the nouns depending on how we use them, like what's their grammatical role in a sentence. And we have 7 such cases. So there is a lot of inflecting of the words, and that's just for singular, and then plural works completely different. And what you mentioned, then it becomes a huge issue for languages like that. Okay, so here we have conjunctions, for example, as well. Will be ideally would be separated as you see it on the right side of this error, but it won't because we are not going to have information that is and not are basically 2 separate units here. If we have hyphenated phrases, they won't be separated as well. And if we have punctuation, it's going to be glued to the last word, which isn't great. So for now, we are going to talk only about the white space tokenizer. Good, not even so good for English, but not good for many other languages. But then later in the semester, we are going to cover much more. Okay, then someone mentioned, all right, so I don't really care about every single word. Maybe I want to filter out some of them. And yes, you can also do pre-processing or text normalization. Again, this is not going to be super relevant for LLMs, but it is going to be relevant for some of these earlier deep learning approaches we are going to cover. So first thing you can do is lemmatization. If 2 words have the same root, you can just keep the root. So for example, plural like dog and dogs, you can decide, well, all occurrences of plural, I'll just transform into a dog. And then I know that these 2 sentences which talk about 1 or more dogs basically talk about a dog. So sang, sung, sings, they are all forms of sing. So you can transform them all into this root form, which is sing. Then stemming, you can decide that you are going to strip suffixes from the end of the word, not the world, the word, such as sing, produce sing out of sinks. You can, if you have a paragraph like that movie review I showed you, you can decide to use sentence segmentation, meaning splitting that text into sentences, and then you can model each individually and aggregate information later on. And then this is where those unimportant words come into play. We call these words that occur too often, like the, and so on, as stop words. And maybe we don't think that these words can discriminate between classes. So both in my positive and my negative review aren't going to have these articles. So maybe I can just remove them such that my classifier has an easier time distinguishing these classes. You can decide whether you were lowercase or not, and so on. And with LLMs, again, we don't need to care for almost none of these, but for these pre-LLM approaches like perceptron that we're going to learn today that you're going to implement, this can have some impact. And by looking at some of these feature vectors today, you are going to see how. Okay, so let's start with the first way of representing pieces of text with features. I'm going to use a whiteboard for this because that's the only way to slow me down from covering this too fast. Let me also make a note to tell you about generalization. All right, so here. Yeah. So. Okay, can I? Bear with me. Let me. Then this light is. Wow. Usually nothing works this easy, so this has been wonderful. Alright, so I'm going to show you how to do one way of producing a vector out of piece of text, and that is going to be called bag of words. Okay, I'm going to use this example. Over here we have 4 separate sentences. So you can imagine this as data with 4 separate data points. The first thing I'm going to do is going to tokenize each one of these with my tokenizer choice, which is going to be a white space tokenizer. So tokenization is the first step. And you tokenize them separately. So you don't, maybe you think, oh, maybe I'm going to merge them in one big piece of text and then I tokenize, we won't do that. Okay, so I'm not going to write how the tokenization with whitespace is going to look like because I feel like we can visualize that. Are you okay with that? Yeah. All right, perfect. So once we do that, we are going to build our vocab. So that's the next step. Construct a vocab. And vocabulary is basically going to be a data structure dictionary where we are going to record words together with some index for that word. And here, let me stop saying word. I'm going to start using terminology token, but because we are using whitespace tokenizer, these are synonyms, okay? But I'm going to use tokens such that later on when we introduce subword tokenizers, we are accustomed to tokens. Okay, so imagine we have split this, each piece of text. Now, from sentence 1, we have this, comma, is, comma, a, comma, good, comma, movie, period, and that's going to be a list we get. Basically, you are going to record each unique token you see from these tokenized pieces of text into your vocab. So now I'm going to do one setting where I don't lowercase I don't do any pre-processing of my of these sentences. So my first token is going to be this capitalized. It's the first token I'm recording. I'm going to give it the index 0. Makes sense to start there. So is 1, a, 2, good, 3, movie, period, 4. And then I check the next sentence. I have good, but now it's capitalized and I have only lowercase version. So I'm going to record it again. Good with 5, movie with exclamation point, right? That's gonna get 6. And then what should I do next? What is the next token I should add? Not, right? And then for maybe people who zoned out for a second, can someone tell why didn't we include this? Yeah. Oh, okay, let's let them hurry because we've already got it. Exactly. Yeah. So this is already here, and our dictionary is not going to have repeated duplicate items like it's a set. So only unique stuff goes here. We have already recorded its index is 0, and we don't need to do it more. Okay. Looking at this vocab list, what makes you a little bit like unhappy about? Like, what would you ideally see differently here? Yes.
Ideally, we want to separate punctuation so we can lowercase so we have unique words actually just be together.
Yes, exactly. So here we have movie period and movie exclamation point, right? If we had a better tokenizer which splits the punctuation from the word, we would have a movie with its own index. We would have a period with its own index and exclamation point with this index. And then later on, we will see why this can have downstream effects. So this would be better. Okay. Anything else?
We have good twice in the vocabulary just because of the lowercase and uppercase.
Exactly. So we decided we won't do the lowercasing and we want uppercase. So now we ended up with two versions of good, where it would kind of be better if you had just one, right? Yeah. That said, why wouldn't then be always lowercase? Well, for example, named entities, names of people, organizations, and so on, they are usually capitalized. And it gives signal to a model that this is a special kind of a book, right? Like, oh, it's a name of something. So you do lose some information by capitalizing. So with pre-LLM approaches, maybe you would use a tool we call named entity recognition. You will find what are the actual named entities, and then maybe you would keep capitalization of that, but keep everything else a lowercase. Okay, now we have a vocab. That was our next step. Okay. All right, and another reason why this isn't like great because we are losing information and some of these are shared later on is now our vocabulary size is larger than it should be. So later we can reuse some computation unnecessarily. Okay, I'm gonna take a photo of this and put it into slides. So do that. Okay, we had our vocab. Can I? Okay. Oh no, I can't lift this one up. Okay, this is a bummer because ideally you would see the vocab while we do this. So it's okay. Let me write the third step. So the third step is actual featureization, turning your text into a vector with features. So turning each SI into some f of SI, where this f is a vector. So the size of our vocab was 8. Don't forget we started from 0. So first thing we are going to define is that our feature vectors are going to be of the size of the vocabulary. So 8, okay? So f of S1 is going to be a dimensional vector. 1, 2, 3, 4, 5, 6, 7, 8. And each one of them all right, so this is going to be element of R8, which is R of cardinality of the vocabulary V, okay? So we use this notation to say what the size of the set is. Now, we define it like this because each one of these dimensions is going to be associated with the token whose index is that dimension. So this dimension is 0, right? And our token that had index 0 in the vocab was what? This, right? Yeah. And we had 1 being is, A, 2, amazing, right?
Good.
Good, let me see. When I was preparing, I was using amazing, but then when I read this is not an amazing movie, I was like, is this positive or negative? Like, this is not a good movie, is really negative, but not amazing. I was not sure. A movie with a period, right? 4, then we have good. It's gonna be 5,
Movie exclamation point.
movie explanation point, thank you, and not right. Okay, so this is why this is of the exact same size as the vocabulary. And now, we have options what to do. We can, for example, record in each one of these dimensions whether this token is present in this given input. So, is token this present in first sentence? Yes, is
Yes.
any good
Yes.
movie period?
Yes.
Good. No, capitalize not. Movie exclamation point.
No.
And not. No. Okay, so this is a feature vector for the first sentence. Okay, so now instead of telling me without me reading tokens, can you tell me 0 or 1 as we go?
0.
Mm-hmm.
0. 0.
Uh-huh.
0. 0. 1.
1.
1. 0.
Perfect. Let's go further.
1. 1. 1.
1. Okay.
1.
All right.
1.
Movie period.
Period.
Yeah. Uh-huh.
0, capital good.
0.
Mhm.
Next one.
0.
Uh-huh. Okay. I'm gonna triple check that. Yeah, great. And then the last one.
1. 1. 1. 1. 1. 0. 0. 1.
Great. I gave you this in exam. You would tell this a trick question. But it has a point. It has a point. Okay, so now, first of all, I want to again say that we have produced that feature vector for every single piece of text we have, and now the goal will be to classify them somehow into positive or negative. But this was the first huge step. So now, do you see any issue here? Something that's not great to see. Oh, again, I needed to let me see something. You're very good, but thank you, Jonathan. Sorry, Sam?
You got lost in positional information.
We lost the positional information, and can you tell it where that is especially problematic in these two examples?
Not being in front of movie,
Mhm.
or in front of good.
Yeah, right. So in sentence 3, what would we say? What is a sentiment of this sentence 3? Like ready to read it out loud. It's
This is not in.
right. Would you say it's like somewhere in between, right? But like maybe slightly positive, right? What about sentence 4? Negative, like 100% negative, right? But what we ended up with, because we didn't model that not occurs in different positions, these sentences is basically the exact same feature representation for things that are very different in meaning, right? And our classifier won't be able to distinguish these two properly. So that's an issue. Do we see a way, let me see, oh yeah, I said we record presence or absence here, so 0 or 1. This is a choice, but maybe the other choices exist. So what else maybe we could have done such that this is not an issue of such severity, such that at least we get some different representations. Yeah, you'll forward it.
You could do frequency of words, so having the 2 nots would be different than having 1 knot.
Yeah, so here, if we, instead of counting the presence or absence, we counted counts of the words, we would see that in sentence 3, where not is, right? Here we would say it's 2 instead of 1. So at least we would get the difference between these two pieces of text and their representations. So I won't do this because it's gonna eat all the time, but maybe try at home, repeat this exercise, but instead of not lowercase, such that you have different vocabulary, and maybe try to record counts to see how different these representations or more similar they would look like, right? So for example, here, the fact that we had good and good, lowercase and capitalized separated, we lost information about similarity of these two pieces of text. If we had lowercase, I would have 1 and 1 here. And then the model understands, oh, these are those examples which have 1 in this dimension number 3, and they were both labeled as positive in the training data. Therefore, I should predict this new example as positive in the future. Because we now have good and good, these ones being at completely different dimensions, the model can't find the similarity between them. Or maybe later in the test set, you would have previously have seen only good, and now you see capitalized good, it wouldn't know what to do. Which brings me to another thing I forgot to mention in slides, and this is, so we typically build vocabulary and everything out of training data. Again, this stems from this test set really being held out. You know, we don't touch it until we are ready only at the very end, which could mean that some tokens you are present in the test set that are not present in your vocabulary. So this can happen with the white space tokenizer. It will not happen with the tokenizer we learn later on for LLMs. So this is again pre-LLM problem, but unknown tokens. So if you encounter token that you don't have in vocabulary, you are going to replace it with some special extra token that you're going to add in vocab. So usually we have we add U and K, and it's going to be then of index is going to be the size of your vocabulary plus 1. And every unknown token you have in your test data that you don't have an index for, you're going to replace with this token. So that's what you're going to do at the test time. I'm going to add that to the slides. Okay, let me take a photo of this to share it with you later. Are there any questions about featurization with bag of words? Okay, cool. So a little bit more about this. I think I covered everything here. We can also extend this idea of bag of words to so-called to representation called bag of engrams, where instead of here we looked at each individual word, and then each individual word was placed into the vocab, right? We can decide to look at the sequences of n tokens, and that becomes a thing in our vocab. So let me get it here. It's going to be useful that let me just show you what n-gram is. This is a super important term. So you must know what the n-gram is. So from our tokenized version of sentence 1, I have this is a good movie, period. Okay, so unigram is basically a word. So what we have just seen is bag of unigram. So 1 gram is called unigram. Then 2 gram is called bigram. 3 gram is called trigram. And then after, we don't have these special words, but we call it 4 gram, 5 gram, and so on. What I've just shown you with bag of words is bag of unigrams, basically. And now what I'm telling you is how you can extend it to n-grams where n is larger than 1. And let's take a case of bigrams. So we are looking at the sequence of 2 tokens. So one bigram is this is a good movie, period. Okay, so sequences of 2 consecutive tokens in a given tokenized input. And we are doing everything the same way we have done before, except now your vocab consists of not individual words, but of these bigrams. So this is will have 0. Is a will have 1, and so on. So you do exactly the same thing as before, except that what you're placing in the vocab is different. You can also combine 2. You can have a combined bag of unigrams and bigrams, where your in the vocabulary is built of the individual words and bigrams. Again, this is one of those decisions, one of the hyperparameters you need to choose. And you don't know a priori what's better. So in machine learning, we don't trust our choice will be the best. Rather, we have a training run where I say I'm going to use bag of words. I'm going to have a training run where I use bag of unigrams, a training run where I use combination. I train my model, I evaluate it on the development set, I see which version is the best, and then I evaluate it on the test set. And that's the final result, I think. Okay. All right, so I also welcome you to try the bag of bigrams for the sentences 3 and 4 in the previous example. This is where bigrams comes into play, because then not becomes a bigram. And not is gonna be often associated with something not really negative in language. It's called, I think, dual negation. Okay, let's cover one more way of pre-LLM way of representing our input document. So this is called TF-IDF. An idea here that some common words like the appear everywhere. So they don't have distinguished text, and distinguishing is crucial if we want to do classification. So in this way, we are trying to circumvent this problem, not by removing these stop words, but rather by introducing concept of inverse document frequency. So let me go over this. Here is a pseudo code of how you can do that. I will work it out just for one of our words to kind of give you a sense what are we calculating here. So first thing we calculate is DF, document frequency of our token, which is over here. It's the number of documents a token occurs in. So if we have DF of this, if you remember, we had 3 sentences that started with this. So the document frequency is going to be 3, because this token appeared 3 times in these, it appeared in 3 out of the documents we had. Next thing we need to define is term frequency. So this is basically what we have already mentioned. It's how many times this token occurs in the first document in our first sentence. What is the count of that? It was only once, right? It was, this is a good movie, it occurred only once. How many documents we have? It's 4. We have 4 sentences, right? And then IDF is defined as a fraction where we have the number of documents divided by the document frequency of that tokens, which is what's n here, just to see whether we are still together. N is how many? 4. And what should I do? Divide 4 with 3. Okay. And then finally, TF-IDF of this in S1 is the term frequency of this in S1 multiplied by its IDF, therefore TF-IDF. And that's going to be equal to, what's the TF term frequency? 1 times 4/3, which is 4/3. Okay, so this is TF-IDF of only one of these terms, tokens in one of the documents. And what we do to build a feature vector is basically we stack this value in an order determined by tokens in the vocabulary, as we did for bag of words. So TF-IDF of the S1 is going to again be vector of the size of the vocab, which was 8. 7, 8, so 8, right? And the first dimension is going to be associated with this. So this has TF-IDF of 4/3 in S1, and this is what we record. So we would again produce the vector of the size of the vocabulary. Is this clear? Okay. All right, so one more thing with TF-IDF is that very often you are going to see this form where the term frequency is squished into a log. The reason why that's done is because if you have, let's say you have term frequency of a token in a document being 1, and then for some other token you have it to be 100. It doesn't mean that this new other token is 100 times more important. So with log, you kind of make that effect a little bit weaker. So you would get 1 and 2, right? So this is why this is done. You will often see this form of TF-IDF. Okay, so other concepts to know here is that basically here, this is all going to be related to a field called information retrieval, where the task, we are tasked with finding the text in some collection that best matches a query. Maybe some search engine application should immediately comes to mind, like when you search something with your favorite search engine, you give a query, and basically we need to find top web pages that are most related to your query. And this is a classic example of information retrieval. So here there is a notion that we are kind of calculating some co-occurrence between words. And this isn't clear yet because right now I was showing you just these feature representations. But imagine I have put this vector here into a column. So now it's a column. Then each word, each dimension is again associated with a token in the vocab. I could do this for every single document I had. So for S2 here and S3 and S4. If I stack them into columns like this, effectively what I have created is this term document matrix, because rows here are all associated with the same token, this, across different documents, S1 to S4. And basically, if you now compare row this with the row associated with token not, you can see how often they co-occur across all of these documents. This is where this co-occurrence is coming from. This is not going to be super important concept for us, co-occurrence or term document matrix, but I did want to mention it because you see it somewhere. Now, that maybe concurrence is a super important term, but what comes next is extremely important. And that's how do we measure text similarity, right? So I'm kind of giving away answer here because it's literally written on the slide and put in bold. It says vector similarity. but maybe can someone say in which way, like a concrete idea of a function you would use to measure?
You like cosine similarity?
Perfect, cosine similarity, couldn't think of a better example myself. So we take two vectors and we measure the angle between them. The smaller the angle is, the more similar they are. The larger the angle is, more dissimilar they are. The reason why we take cosine and not just dot product, for example, is because we don't really care about magnitudes of these vectors. We just care about their, like, how far away are they from each other. If we had the dot product and these weren't unit vectors, then the magnitude would have an interplay with the similarity, which we do not care about. So yes, now that you have these, you can do it both for terms, tokens, and for documents. So you can measure how similar S1 is to S2 by comparing, measuring cosine similarity between the feature vectors of S1 and S2, right? And you can measure how similar tokens this and not are by comparing these rows based that we have created by stacking these vectors, which we won't do often. This is not important. So now going back to my example of information retrieval and retrieving a document, can you walk me through? Can you give me a process of how, given a query, and let's say my collection of 10 documents, what would you do to find the document that's most relevant for my query, given the methodology we have at our disposal after the time we spent in this class so far? Yes, please.
I would find the biggest similarity between the query and documents that I have.
Exactly. So you would measure then cosine similarity, right? And find which one, basically rank them based on the cosine similarity and retrieve the one that is the most relevant or show them all in the orders they are. So I think this is kind of cool that with very simple methodology, no machine learning yet, just producing these feature vectors using cosine similarity, ranking documents by vector cosine similarity, we can do this task of information retrieval, which has really real applications like search engines, right? So very cool. Okay. So this brings me to the end of just 1 out of 4 components of machine learning I want to cover, which is a feature, constructing a feature vector representation. Let me just go over bits and pieces again. So we start with a piece of text. And we can't wrangle these texts as a string. We need to produce some vector representation. And as of now, we have seen 3 ways we can do that with tag of words, tag of engrams, and PFID. In all these 3 cases, what we have produced is the vector, feature vector of the size of the vocabulary. And we constructed the vocabulary out of tokenized data of each of the examples in our collection. And then we were counting things like presence or absence of a token, count or frequency of a token, and with TF-IDF a little bit more complicated way that accounts for some of the situations we would like to catch. And now, just as a kind of next thing we are going to talk about, it's going to be next component is to see what to do now with these feature vectors. We are going to define a model which will be based on a function called sigmoid function, which will give us this notion of probability. Then we are going to go over what negative log likelihood training is. That's going to define our objective. And then finally, we are going to define an algorithm, which is going to be stochastic resolution, to change parameters of our sigmoid-based model to have a good solution on the training data that hopefully then generalizes on it. So I hope to cover all of that next time. Okay, we have 5 more minutes, so are there questions? Please don't start to back yet. So far you've been having good questions, so let's see. Yes, please.
Can you give idea of method how, that these numbers are, encoding the meaning of the sentences? We got a number 4 for this, and we get other numbers like that. How is all these numbers actually encoding the meaning of something in the future?
Yeah, so the question is, how do these vectors encode the meaning? And let's maybe go over here. So, here. Yes, we are kind of focusing on, just the surface form of the words. And basically, we are capturing meaning by measuring whether something is present or absent. But, and then this helps us see, tell whether two pieces of text are similar, because if there's a lot of concurrence, then they are not similar. So in this way, we capture similarity in meaning. But if your question is to hint that this is very rudimentary way of attempting to capture meaning, you will be completely right. Because, for example, these approaches can't capture any sense of relatedness, right? So remember when I told you that eventually, very soon, we are going to start to talk about embeddings, which won't be representations that are constructed by in this way, but rather data to learn from the data. With those word embeddings, I showed you that the most related word to the word pecan was poppy, right? And this is something you can't get out of a model like this, right? With these back of word stuff, because pecan and poppy are going to be constrained to different tokens, and they are going to be correspond to completely different dimensions. So, if that's what you wanted to say, yes, you would be right that these are very shallow approaches, but for some of the tasks, words already give a lot of hits, right? Like when we reduce these words on their own already hint on what's going to happen with the sentence of this review. So for some tasks, you don't need much more than that, and you will see when you implement this that you can achieve reasonable accuracy over 70% within context. Okay, let's move on to Jenna. Yeah.
Right, I wanted to know, like, how is it making the TF-IDF is making the feature vector representation better efficient?
TF-IDF, well, TF-IDF is fixing this issue of basically stop words. We know that some tokens appear in many different texts, and they don't have what we would say discriminatory power to tell us this piece of text is different from this one, because they're going to occur in both of them. So there is with TF-IDF, we have this IDF term, we kind of handle that. If a term has occurred only in one document, so it has super strong discriminatory power because it's unique to only one document, then IDF will be huge. It's going to be n/1, right? But if you have a token that occurred in all of the tokens, it's going to be n/n, and it's going to be 1. So you're going to penalize it for being very often, occurring very often. And of course, you can say, well, couldn't I just remove stop words? You could, but then maybe you're losing something else. So this might be a safer. Yeah.
Are you labeling any of the data during any of this, or is that?
Yeah, no, we don't do labeling here. So labeling, we assume here we didn't use labels. That's first of all. But your data is something you get obtained from someone else, or maybe you construct it, but more often you get it from someone else. And some people, some annotators have annotated those data with labels. But so far, we have focused only on the input part, and we haven't used the labels in any way. Anyway. Okay, Mary, I'm going to stick around a little bit more if you have more questions. Thank you.